This presentation is part of the Basic Electrophysiology program. It is meant to be an introductory lesson for people who are learning cardiac rhythm interpretation. This particular presentation is going to cover the bumps and squiggles of the electrocardiogram. I will describe each of the waves found on the electrocardiogram, and I will also discuss some of the intervals utilized when interpreting a rhythm strip. After this presentation, I will be using all of these terms when diagnosing all 6 classifications of cardiac rhythms. So as you can see today, what we're going to discuss is we're actually going to talk about the P wave, the PR interval. We're also going to discuss the QRS complex and why it's called a QRS complex and not called a QRS wave. We're going to discuss the ST segment. We're going to discuss the T wave and its shape and importance. We're also going to talk about something called the PR interval. There's not an interval behind that, but that's supposed to be PR interval. And we're going to discuss a little bit about the QT interval. There's also going to be a couple of other intervals we're going to discuss. One of them is going to be the P to P interval. And we're also going to talk about the R interval. So first, let's start off with discussing baseline. This is also called the isoelectric line. These two terms right here are kind of synonymous when we talk about baseline and the isoelectric line. So what happens at baseline is that you see this line right here that starts out right there and then goes all the way across over here. This line is considered baseline because at this point here during baseline there is no electrical activity going on in the heart right now, which means it has completely repolarized or it has completely depolarized. What's important about baseline is that this is where a lot of our measurements begin. So if you want to find a P wave, for example, you have to start with the first rounded bump here starting from baseline. Also, so it'll tell us this way, it'll tell us time this way, or it'll tell us distance this way, and this is kind of where we start off with everything. So if we want to find out how many millimeters up the QRS complex goes, we start at baseline. If we want to find out how far the P wave travels and what time frame, we use baseline, and we start right here at the first deflection away from baseline. So this is something that you're going to hear several times. When I talk about wavy baselines or bad baselines or an isoelectric line, where is the isoelectric line? This is what I'm referring to. So the first part of the electrocardiogram I'm going to discuss is going to be the P wave. What the P wave truly represents is depolarization of the atrium. This is what the P wave actually means. A lot of people, and I will say this too, is the P wave signifies SA node depolarization, but that's only partially correct. That's not entirely accurate. There are a lot of rhythms that begin in the atrium, and you'll have a P wave. So atrial depolarization is what the P wave stands for, or represents, but most of the time for a sinus rhythm, the P wave will mean SA nodal depolarization. As you go further along in this program, that'll make a little bit more sense, but you do need to know that what the P wave truly means is atrial depolarization. The duration of the P wave should be 0.10 second or less. The shape of the P wave should be smooth, round, and typically upright. in this case, you want to look here. I don't have a grid on here, so you can't really tell, but it is smooth, it is round, and it is upright, and it should be, the P wave itself from here to here should only be about 0.1 second. Since this P wave represents atrial depolarization, there is an atrial repolarization. You don't see this very often, if ever at all, because it's such a small repolarization that there's not a lot of voltage there. There's not a lot of electricity here. So what happens is you might see a TP wave if there is atrial repolarization, but notice here it's buried in the QRS complex. So even if the atria does repolarize and you do have something here, the QRS is going to mask all of that. So some people ask, is there a repolarization of the atrium? Yes, there is. Is there a wave for it? Yes, there is. It's called a TP wave. Just nice to know information. Now let's discuss the PR interval. The PR interval represents the time it takes for the electrical current to reach the AV node, get through the AV node, and reach the His bundle. So it represents the time it takes for the signal to reach and get through the AV node and then reach the Purkinje network. The PR interval is measured from the beginning of the P wave and stops at the beginning of the QRS complex. Now the duration of the PR interval is very important because this may change your rhythm interpretation. The duration of the PR interval goes from 0.12 to 0.20 second. If it is outside of this range, that means that there's something else going on. This we will discuss later on in junctional rhythms, and we will also discuss a little bit about this in ACS imitators and early repolarization, and early depolarization. So we're going to discuss that way later. All we need to know right now is that the normal PR interval goes from 0.12 to 0.20 second, or you could say from 3 to 5 little boxes. There is another area down here that I want you to look at. This is called the PR segment right here, different from the PR interval. The PR interval, as you can see here, starts here at the P wave, ends at the QRS complex, but there is something called a PR segment that begins after the P wave and ends at the QRS complex. This PR segment here becomes important later on when we're talking about diagnosing some other stuff, like, for example, pericarditis has a depressed PR segment. So you have to know, if you see something that says there's a depressed or elevated PR segment, that means that you have to look at just that little area right there. I want to discuss just a little bit more about the PR interval. This is a pretty good picture that I have here about what exactly happens during the PR interval. As you can see here, the green color, this part right here is SA nodal depolarization. So in this case, the P wave, which represents atrial depolarization, we say comes from the SA node, shows you that the atrium is truly depolarizing here, causing the P wave, or vice versa. So here you have the red line here, or the red color here, which is atrial depolarization. So this is the depolarization of the atrium. The SA node just initiated this atrial depolarization. Now the AV node here, this is where the AV node is actually received the signal. So you have the signal right here. Look how much time it took for the signal to reach the AV node. It doesn't take very much time at all. So once you have that SA node and those internodal pathways in that AV node here, when the signal travels down these superconductive pathways, as you can see here, it doesn't take very long for that signal to reach that AV node. So the AV node has to slow that signal down to allow for this wave of depolarization to reach all the way across and all the way throughout all of the atria, through both atria. So as you can see here, this is the importance of the AV node holding the signal. Now, at the same time, the atrial depolarization right here occurs. This is a much slower system for it to happen. Once the signal gets through the AV node down to that trigger zone, if you remember the trigger zone, once it reaches that trigger zone, then the signal will travel through the His bundle, through the bundle branches, and then finally terminate at the Purkinjes. So what happens here is during this whole PR interval, after SA nodal depolarization, you have to account for atrial depolarization. Then you have to account for the bundle of His. Then you have to account for the bundle branches. Then you have to account for the Purkinje networks to actually receive the signal. This whole process has to occur right here just for the ventricle to depolarize. So you can see if it's taking longer than 0.20 second for the signal to get down to the Purkinje network, there's a delay somewhere in here. At the same time, if you want to see, or if you understand that the minimum time that it should take is 0.12 second, this is why it should not take less than 0.12 second for that signal to go down there, because it has all of this stuff here that has to occur before it can depolarize the ventricles. So now we've made our way down to the QRS complex. Now notice that this is not called a QRS wave, it's called a QRS complex. Now the reason that it is not a QRS wave is because a QRS complex is actually made up of a Q wave, an R wave, and potentially an S wave. And I'll describe what each one of these are. Now the Q wave of the QRS complex is the first negative deflection following the PR interval. So as you can see here, we have our P wave here, we have our right here to right here. This is all the PR interval. This is the first negative deflection following the PR interval. This is classified as a Q wave. Now an R wave is defined as the first positive deflection. Following, and it's either going to follow the Q wave or the PR interval. The reason I say that is because you might not have a Q wave, and it might be okay that you don't have a Q wave. So it's very possible that you could have a PR segment right here, your PR interval, and then it bypasses the Q wave and it goes directly up, and it is the first positive deflection. So it's still classified as an R wave because it is the first positive deflection following the PR interval. The last wave that you're going to have is something called an S wave. Now the S wave is a little bit more complicated, but not too much. The S wave is the first negative deflection following the R wave, but there's an extra piece of criterion that goes along with this. In this case, this S wave must extend below baseline. So an S wave must go below baseline. So in this case here, what we have is we have a Q wave, we have an R wave, but notice that we don't have an S wave because technically on the picture that does not go below baseline. So this would be called a QRS complex, but if you wanted to be specific, you would call it a QR wave, even though it's called a QRS complex. So just to give a little bit of examples here, let's say you have a P wave and then you have, it goes up, it goes down, and then it goes into your T wave. The type of QRS complex this would be is you have an R wave and you have an S wave, so this would be an RS wave. So you can see there's a little bit of difference here. They're all considered QRS complexes, but they are not all the same shape. Another thing you could have is you could have a P wave with a very small up and a very big downstroke, and then it comes back up and goes into a T wave. By looking at the definitions up here, this would be an R wave and that would be an S wave, but this would be a little r with a big S wave. You could also have, when you get into bundle branch blocks, you could also have a P wave and you could have it go up, down, and then up again, and then back down here, and then this right here, there's your T wave. So this would be an R prime S wave. That would be an R prime S. What happens if you have a P wave here and it goes up, down, up, and then back to baseline, and then like this? This would be an RS R prime. So as you can see, you have a whole bunch of different little options here. So when you talk about describing the QRS complex, sometimes you really do have to be that specific and say you have a QS wave or a there's another one, QR wave. Here's a good one. What happens if you have a P wave and it goes up, down into a T wave like that? That's classified as an RS, although there's no R, or I'm sorry, although there's no S. And here's another one here. If you have a P wave and then it goes down and then back up, and then a T wave, that's actually called a QS wave. I didn't make that stuff up. It's just the way that it's commonly called. So either way, these are both called QRS complexes, obviously. But if you want to try to describe, you say, ooh, look in this lead right here, we have an RS wave. That's what they're actually trying to describe. Now that I've explained the waves a little bit, I just want to talk very briefly about the shape and duration of the QRS complex. The shape of the QRS complex should be narrow, should have steep angles, and should have sharp points. If at any time you do not have a narrow, steeply angled, sharply pointed QRS, that means that there's something else going on. Another thing about the QRS complex is that it is supposed to be less than 0.12 second. Some of the other literature says less than or equal to 0.1. I use the less than or equal, I use the less than 0.12 second because that's kind of what American Heart uses. Well, it is what American Heart uses. So I just stick with what they use. That's kind of considered the standard. And you begin that measurement right here at the beginning of the QRS complex, and it ends right here at something called the J point, which is what we'll discuss next. The J point, as you can see, this little area right here, represents the spot where the QRS complex ends and the ST segment begins. That's what the J point represents. And I think I read somewhere the J stands for junction point. It's the junction between the QRS and the ST segment itself. Most of the time, it should be, the J point should be at baseline. Should be located at baseline. Although there is literature out there that says that there's a 1 millimeter variance, which basically means the J point can be about 1 millimeter high or 1 millimeter low, and it's considered a normal variant. It's considered, it's normal, it's not any problem, it's just, for some reason, it's just 1 millimeter off. Now, if you get past 1 millimeter and you have it in what's called contiguous leads, which is in the 12 lead part of this program, then you can say that there's maybe an emerging heart attack of some kind of cardiac ischemia going on. But just understand that 1 millimeter is a normal variance typically for the J point. And that's a variance from the isoelectric line or baseline. Now let's talk about the ST segment. I just mentioned something about the ST segment. The ST segment is this part right here, this red part right here. And what it represents is the time between ventricular depolarization which is the QRS complex. I forgot to mention that earlier. The ventricular depolarization is the entire QRS complex. That is when both ventricles depolarize. So the ST segment is the time between ventricular depolarization and ventricular repolarization. It starts down here at the J point and terminates at the onset of the T wave itself. Normally it is approximately less than 0.12, I'm sorry, that's a mistake. It is less than 0.20 second, but it's also heart rate dependent. Which means faster heart rates are going to shorten the the ST segment. Slower heart rates are going to draw out the ST segment. Ideally, though, it should not make that much of a difference how much away from 0.20 second. Also, the ST segment should be at the isoelectric line. It should be at the isoelectric line just like the J point. Typically, this also has a 1 millimeter variance. So you could be a little bit high, a little bit low, and it means perfectly, it's just perfectly fine. Nothing wrong with it. Next, we're going to talk about the T wave itself. The T wave, first of all, the T wave represents ventricular repolarization. It is measured from the deflection away from the ST segment here and ends when it comes back to baseline. Now, if you look at the ST segment, it has a specific shape to it. The ST segment, as you can see here, has kind of a slow upstroke, and then it'll have a more rapid downstroke. Okay? Now, this ST segment here must be asymmetric. So it has a slow upstroke and a fast downstroke. If it is symmetric, symmetry in T waves is a bad thing. It could mean a few things. It could mean an electrolyte imbalance. It could also mean head injury. It could mean cardiac ischemia of some kind. So symmetry in T waves is bad. They should always be slow upstroke, fast downstroke. You can use the absolute and relative refractory periods for ventricular depolarization and repolarization with this too. The peak of the T wave is the dividing line between ventricular absolute refractory period, which means that it cannot respond to another stimulus, and relative refractory period, which means it can respond to another stimulus. What happens is whenever the T wave reaches baseline and you start this isoelectric line right here, now this is considered resting. We're going to go ahead and talk about some intervals now. We went through all of the little intervals, a couple of the intervals, and all the different waves and points. This is all the important stuff. Whenever you want to talk about interpreting a rhythm, all of this stuff here, the P wave through the T wave, that's all the really important stuff. But the further along you go in this, you will also end up learning a few more intervals. So I'm going to go ahead and discuss the intervals now so that when we discuss them later, they won't be quite so foreign whenever we start discussing them. I will review these again later, but it's a nice little exposure. The first interval I want to discuss is called the QT interval. This is a very common interval that is utilized throughout higher levels of healthcare. When we look at 12 leads, there's a way to calculate the QR interval based on a heart rate. Fortunately, now the circuitry and computer technology has achieved a point where it does it for us. All we have to know is kind of what's normal. It will even interpret on a 12 lead prolonged QT interval or shortened QT interval. So the QT interval basically represents all of the ventricular activity. So as you can see here, it begins at the QRS complex and goes all the way through the ending of the T wave. So it represents the QRS complex, which is ventricular depolarization, and it also has the T wave, which represents ventricular repolarization as well. Now the duration of the the duration of the QT interval usually ranges from about 0.36 to 0.44 second. And that's the normal range. Once again, just like the ST segment, this QT interval here is heart rate dependent. Very heart rate dependent. Sometimes what you will see is something called a prolonged QT interval. The problem with prolonged QT intervals is that you are actually drawing out the relative refractory period. Now the relative refractory period, if you remember from a previous lesson, is the time when a cell or the heart can depolarize to another impulse, but it is a very unstable time for the cell or the heart. So if another beat hits right here in this relative refractoriness, which goes from the top of the T wave down here to the resting period here, then it could send the person, theoretically, into a ventricular rhythm, which is a pulseless ventricular rhythm like torsades, VFib, that kind of stuff, pulseless V-tach. So if you have a prolonged QT interval, your relative refractory period also prolongs out as well, predisposing the person to life-threatening arrhythmias. Couple more intervals here and then we'll be done. So first of all, let's talk about the U wave a little bit. The U wave is very commonly seen after the T wave here. So you have your T wave here, and then you have this extra little bump after the U wave. Generally speaking, when it comes to the U wave, there's no clinical significance. Which means some people have U waves. It doesn't mean that anything is critical going on right now. You have to kind of do a little bit more investigation into what's going on with the person to really figure out if there's something going on with the U wave. Now there's a couple theories out there about what it could be. It could mean that there is some type of extra repolarization, so like an endocardial, an extra endocardial repolarization. Sometimes the U waves are actually seen in the early stages of hyperkalemia. So that's another time or another possibility why you might see a U wave. The problem with the U wave is that sometimes the computer on the EKG machine, when it is interpreting the rhythm, will not see the end of the QT interval as right here. It might see the end of the QT interval as right here. And if the computer reads this as a QT interval, which it isn't because there's a U wave, then it's going to diagnose this as a prolonged QT. But if you know what you're looking for on the 12 lead and it says prolonged QT interval and you see an extra U wave down here, then you know that it's an incorrect interpretation. You just know that, well, the T wave is probably here, or the QT interval is here, therefore it's probably normal. Now, a couple other intervals I want to talk about is the R to R interval and the P to P interval. The R to R interval is pretty simple. It is the distance between two consecutive R waves. Pretty easy. The P to P interval is the distance between two consecutive P waves. That's pretty simple as well. When we start talking about regularity of rhythms, we start looking at the P to P interval and the R to R interval. When you start talking about interpreting heart rates, for example, you can use the R to R method. And it really becomes important understanding R to R and P to P intervals when we start talking about heart blocks. So if you have a person who is having a heart block, I'm going to discuss how P to P intervals are normal, but the R to R intervals are not normal, how they're not regular and stuff. So those are the other two important intervals that we'll talk about also. One more thing I would actually like to mention before we get done with this whole thing, and I've been asked this question before, and I like to just kind of throw this out there because it's pretty neat information, and I happened to come across this information, and I thought it was pretty cool, is a lot of people have asked me in the past, where does the P, QRS, and T wave actually come from? A lot of people say, why did they start with P? Why didn't they start with L or something along those lines? So I stumbled across the answer a long time ago, so I'm just going to talk about this right quick. Many, many years ago, whenever they were first doing all of this research into the electrocardiogram, and this was actually about the time as Willem Einthoven, and around that time, a little bit before his time too, a lot of the people who were doing this research were not just physicians, they were also mathematicians. They were people who were scientists, who maybe might have worked in medicine, but they were also doing a lot of research and all kinds of stuff. And they were looking at these waves. As they were starting to detect the cardiac electrical impulses on the surface of the skin, they knew that they had to label these things somehow. And there was a lot of debate on how to actually label these. So they decided to go ahead and start using letters. Now, they couldn't really start with the beginning of the alphabet, which is letter A, because a lot of the mathematicians and a lot of the people doing this, a lot of the theories that they use in math are using the beginning of the alphabet anyway. So, for example, you couldn't use A because A squared plus B squared equals C squared, example, for a Pythagorean theorem. So a lot of these letters were already taken. So you couldn't call it an A wave because A's were already used in a lot of these theories. So they decided to go ahead and start using the second half of the alphabet. Now, the beginning letter of the second half of the alphabet that we use here in America is the letter N. Well, they couldn't use the letter N because statisticians were using this as the number of the sample group. So if you have a research and you're doing this research and you're saying, okay, we're going to test 113 people on your publication, you would put N equals 113. So we can't use N because that number or that letter is already taken. The next letter in the alphabet is O. Well, we couldn't use O. They didn't use O because O is the origin on the Cartesian plane. So if you have the Cartesian plane here and your little dot right here, that's 0, and then you have numbers this way and then you have numbers this way, you couldn't use O because O stood for the origin. The next letter in the alphabet is P. And that's where they started with, was the P wave. And then you have the Q wave, R wave, S wave, the T wave, and the U wave. So that's actually where this all came from right here. So if anybody ever asks, where did the P, Q, or S, and T come from? Now you can explain it to them and sound even smarter. I hope you enjoyed this presentation about the QRS complex, the P wave, the T waves, all the little bumps and squiggles with this presentation. If you do have any questions, please feel free to contact your lecture instructor.